In this module, we learned to create a confidence interval to estimate a population mean based on a sample mean. The ideas are very similar to confidence intervals for proportions. The table below will highlight these similarities. We will study this table to make connections between what we have already learned about the confidence interval to estimate a population proportion and what we are learning now about the confidence intervals to estimate a population mean. That's the difference. Remember, population proportion, that was for categorical data. And now we're doing population mean, that's for quantitative data. Okay, so the concept here, when we take lots of random samples, we use standard deviation of the sample statistics to describe the error that is due to random chance. This is called the standard error. The standard error depends on a population parameter and size n. And we saw this for sure. The standard error is the square root of p times 1 minus p over n, where p is the population, or sorry, the sample proportion. Or no, I'm sorry, the population proportion, and the standard error is sigma over the square root of n, which is the standard deviation over the square root of n, the sample size. And then on the other hand, if a normal model is a good fit for the sampling distribution, then 95% of the sample statistics estimate the population parameter within two standard errors. That describes the margin of error. 95% margin of error, it was two standard errors, 2 times this formula. 95% margin of error was 2 times the standard error. And again, this is for means. So the first column is for proportions. This is what we've seen already. And this is what we're kind of working on now. This is old and this is new. So we have sigma over the square root of n. That's kind of a new thing for the last couple modules. And now 95% margin of error, we're going to use now 2 times sigma over the square root of n, as opposed to the big formula, 2 times the square root of p minus 1 minus p over n. Now the confidence interval used to look like p hat, the sample proportion, plus or minus the margin of error, but now we have the sample mean, x bar, plus or minus the margin of error. And just more specifically, because the margin of error is sigma over the square root of n, it's the sample mean x bar plus or minus 2 margin of errors, which is sigma over square root of n. These confidence intervals require a normal model, so we can only use these formulas when the normality criteria are met. In the old stuff that we've done in the previous unit, both the expected successes n times p and the expected failures n times 1 minus p are at least 10. That's what we had to check. Now we check variability is normally distributed in the population. If you kind of graph it out and you see that it looks like basically a normal distribution, or as long as the sample size n is at least 30. So we saw that in the previous module, that it seems like no matter what's going on, as long as your sample size is bigger than 30, then you should be good to go and you can just use a normal model. But if your sample size is smaller than 30, you should plot out the data and see if it looks like a normal model. Let's see, scroll down. Now at this point, we'll make a comment. Let's see. You may remember that we adjusted the standard error by replacing the population proportion p with the sample proportion p hat. Doing so made sense because the goal of the confidence interval is to estimate p. Therefore, it's odd to assume that we know p when calculating the standard error. When we made this adjustment, the margin of error in the confidence interval formula changed. Here's the adjusted formula, p hat plus or minus 2 times the square root of p hat times 1 minus p hat over n. It looks like the old formula, but now we're using p hat instead of p, the sample proportion instead of the population proportion. This adjustment changed the normality conditions. We use the adjusted confidence interval to estimate p when the successes and failures in the actual sample are at least 10. We will eventually have to adjust the standard error for the sampling distribution of sample means too. It makes sense because in many situations, we will not know the population standard deviation sigma. This adjustment is more complicated than the adjustment to standard error for sample proportions. So before we do it, let's practice finding the confidence interval for mu, assuming we know sigma. We can realistically assume that we know sigma when a lot of previous research has been done. For example, when we're estimating height, weight, or scores on a standardized test, previous research gives us reliable values for sigma. In the future, we'll see where if we don't know sigma, there haven't been a lot of studies done on the topic, whatever the topic may be, and we don't know sigma, then we'll see what to do. But for now, we'll assume it's a topic that we've done, that there's been research on, and we know some kind of sigma from a previous statistical study. So one could be estimating the mean SAT math score. So the SATs have been going on a long time. The mean score for math hasn't changed much in the last certain number of years. So we'll just assume that the standard deviation is the same now that it was 5 or 10 years ago. The SAT is the most widely used college admissions exam. Most community colleges do not require students to take this exam. It's just universities. The mean SAT math score varies by state and by year. So the value of mu, the mean, depends on the state and the year. But let's assume that the shape and the spread of the distribution of individual SAT math scores is in each state is the same each year. More specifically, assume that individual SAT math scores consistently have a normal distribution with a standard deviation of 100 in the state, regardless of year. So we're specifying certain state. We haven't said which one yet, but assume that in this state, the standard deviation is 100 in that state. Let's see, an educational researcher wants to estimate the mean SAT score mu for this state in this year. The researcher chooses a random sample of 650 exams in his state. The average score for this sample is 475. With that, we'll estimate the mean SAT score in the state for this year. We got to make sure we can check conditions though, make sure that works, and then we can use the formulas that were outlined above in that table. From our previous work, we know that a normal model is a good fit for the distribution of sample means from random samples if one or two conditions are met, or sorry, one of two conditions are met. The population of the individual values is normal, in which case the sample size is not important. If we do not know the population of individual values is normal, then we must have a large sample size, more than 30. Because we assume that the distribution of individual SAT math scores is normal in this example, a normal model is also a good fit for the distribution of sample means. Now we'll look for the margin of error. Keep in mind that the sample mean x bar is only a single value estimate for the population mean mu. Because it comes from a random sample, we expect there to be some error in the estimate, but how much error should we expect? We know that the sample distribution of means is approximately normal because conditions are met. Recall that in a normal model, 95% of the values fall within 2 standard deviations of the mean, so we use 2 standard errors for a margin of error. The standard error is sigma over the square root of n. Sigma over the square root of n is sigma, they said, was 100 over the square root of n, and n is 650. If you do on your calculator 100 divided by the square root of 650, it's about 3.9 if you round it. So the margin of error is twice that. Standard error is 3.9. You double that. 2 times 3.9 is 7.8. Okay. So you found the margin of error. Okay. Now we'll move on. We'll find the confidence interval and then summarize what we've learned here. We are 95% confident that mu and x bar, the sample mean, are within 7.8 points of each other. That was 2 times the standard error. So we construct a 95% confidence interval from the sample mean by adding and subtracting 7.8 points. So they said that the sample mean was 475. We'll add 7.8. That gives us this larger number, 484.8. If we take 475 and we subtract 7.8, we'll get the smaller number, 467.2. So that would be our confidence interval. We're 95% confident that the true population mean falls somewhere between 467.2 and 484.8. As it says here, yeah, that the mean is between them somewhere. We're 95% confident. Recall that from our previous work, that being 95% confident says that this method in the long run produces an interval that captures the true population mean about 95% of the time. In summary, if we want to estimate mu, the population proportion, or sorry, the population mean, we want to calculate a confidence interval. The 95% confidence interval is this. This is a good formula to write down if you haven't already, somewhere in your notes. X bar plus or minus 2 standard errors, but the standard error is sigma over the square root of n. We can use this formula only if a normal model is a good fit for the sampling distribution of sample means. If the sample size is large, and by large, as we said before, n is greater than 30, we can use a normal model. If the sample size is not greater than 30, we can use a normal model only if the variable is normally distributed in the population. As always, we must have a random sample. If the sample is not random, we cannot use it to estimate mu. We say we are 95% confident that the interval contains mu, which means that in the long run, 95% of the confidence interval intervals contain mu.